In this video, we will be looking at two applications that use a radian measure that we talked about in the last video. And the two applications are linear and angular speed. So first we'll define what they are. The linear speed has to do with a line or a measurement that in this case is on the outside of the circle. And we're looking at a point that is moving, in this case, around a circle. We're giving that point the variable p. And we're looking at the distance that it's traveling over a particular amount of time. You know this calculation from things that you've done before when you're going on a road trip, for example, and you're trying to figure out how much time it's going to take for you to get there. And you're looking at the amount of miles that you traveled divided by the number of hours. So that'll be the overall speed. We use the variable v to denote speed, or in this case, velocity, which is another word that we use. And then s is the variable that's being represented for the arc length, and that matches up with what we were seeing in the last section. So s has to do with the length of the arc. And then, of course, t is for time. So we're just asking ourselves, as this point moves along the circle, how quickly is it going? Angular speed has to do with how quickly this angle is moving or opening. If you think about maybe a bicycle that has spokes and how quickly those spokes are moving around the circle at a particular speed that they're traveling. And so that has to do with the angle that is created partially by that point that's on the circle, and then also having some, in this case it's the origin, but the vertex of the angle. And then b would be the starting point. We use this letter here is a Greek letter. It's called omega to denote angular speed. And then this is theta, also a Greek letter that we're using for angles. And then t, of course, is time also. So here are the two main formulas that we'll be using to calculate angular speed and linear speed. And these two formulas down here are showing how we can take information and translate them back and forth to one another. We know that arc length is based on the radius, and so this substitution, s equals r theta, came from our last chapter, I think, or the beginning of this chapter. And then we're taking a different substitution. We're taking theta and time, and we're substituting it for omega from this here. So this is a way that we can kind of translate back and forth between the two different formulas. So let's do a couple of example problems. We have a point on a circle with radius of 10. Let's draw a picture here. So we know that the radius is 10. We've got some point somewhere on the circle, we'll call it P. So there's an angle that's created, and our angle is here. And then, of course, S is our arc length. We're calling the origin letter O. And based on the picture that we had before, the B was what we had here as the, sort of the starting point of our angle, the initial side. So the ray, they're talking about this side, the terminal side of the angle, is rotating with an angular speed of pi over 18 radians per second. All of the applications will have radians as the measurement for angles. We want to find out the angle that is generated by that movement in 6 seconds. So that's asking us to look at angular speed. So for part A, we're trying to find the angle, and we know, because they gave it to us, the angular speed. They told us that the angle was moving at pi over 18 radians per second. So the original formula we had was that omega is equal to theta over t, but we're trying to find what theta is. So if I multiply both sides by t to rearrange this, I can have t times omega equals theta. We know that the amount of time is 6 seconds, so we'll put 6 seconds. And then we have omega is pi over 18 radians per second. And since I have the same units that are canceling, I'm going to end up with 6 times pi over 18, or pi over 3 radians. So again, that's the angle that is being generated every 6 seconds. This angle is going to open by pi over 3, which, as we know from things that we were learning before, that's going to be about 60 degrees, right? 180 divided by 3. All right, part B is asking us to find the distance traveled by that point along the circle in 6 seconds. So that's going to be relating to the arc length. So we know that arc length is equal to the radius multiplied by the angle. And in part A, we found that theta was pi over 3, right? And we know that the radius is 10 centimeters. Let me move this over. So I have 10 centimeters multiplied by pi over 3. And again, this is asking us to find the distance traveled in 6 seconds, but this answer that we found was related to 6 seconds, right? So we already know that this is the angle that's generated in 6 seconds. So this will be the length created in 6 seconds also. So it looks like we end up with 10 pi over 3 centimeters. And then part C is asking us to find the linear speed of p in centimeters per second. So now we're trying to find the linear speed. We know that velocity or speed is going to be the arc length, the distance traveled divided by the time. So velocity equals distance over time. We found that the distance traveled was 10 pi over 3 centimeters. And the amount of time is 6 seconds. So in your calculator, type in 10 over 3 and then divide that by 6. Grab my calculator. And you should get 5 over 9. Again, we're doing these calculations, don't include the pi symbol, and we'll just have it kind of hang out there. So we'll put that the velocity is 5 pi over 9 centimeters per second. All right, let's do a different example. This example has more of an application rather than just being some random point that's moving around. a bicycle wheel or something. This is a pulley system where we've got this belt that's wrapped around the outside. And it's telling us that the belt runs on a pulley. The radius is 6 centimeters, and it's moving at a speed of 80 revolutions per minute. We want to find the angular speed of the pulley and then also the linear speed. So again, the angular speed is going to be how quickly this angle is opening versus how fast a point is moving on the edge. All right, so for part A, we know that in 1 minute, the pulley is going to have 80 revolutions. And for each revolution, is 2 pi, right? Because if I start at a point here and I go all the way here would be pi, all the way around the circle, that's going to be 2 pi. So we're talking about what is the change in the amount of radians in that time. So let's do this. We're going to do 80 revolutions for every 1 minute. And then I'm doing a unit conversion here. That's going to be 2 pi radians for every 1 revolution. Right, so revolution and revolution will cancel. And so then if I multiply across here, I'm able to see that I'm getting 160 pi radians per minute, per 1 minute. But this is asking me, for part A, it's asking me to know the number per second, right? So what I would do instead now is just maybe go one step further and say, okay, there are, in every 1 minute, there's going to be 60 seconds. So then I'm ending up with 160 divided by 60 will give you 8/3 times pi radians per second. That's one way to do the problem. Let's go back for a second. Let's go back to this step right here. When I had that radians per time, radians per minute, that's how fast the angle is moving, right? So that's, we could say we have 160 pi is equal to theta. And the time was 60 seconds. So another way to think of this is omega equals theta over t. 160 pi divided by 60, and we'll end up getting that same answer. So the first way we're doing unit conversion, the second way we're using that formula that was given to us. All right, the second part of the question is asking us to find the linear speed. So if there was a point sitting on the outside, or maybe a particular point on the belt, right, that's moving around the pulley. Say there was a point here. How fast is it? How long? What's the speed of that going around the outside? So for part B, we're going to use this calculation instead, because we just found omega and we have the radius. So again, going back up to our formulas, we have a number of different options here. We're trying to find the velocity or the speed. And I have 3 different formulas I can use, but I already know the angular speed and I know the radius, so I'm going to go to that version because that helps me based on the information, the other information that I have. So the radius again was 6 centimeters. And then we found the angular speed to be 8 pi over 3 radians per second. So our velocity ends up being 16 pi centimeters per second. All right, if you have questions, you can send me an email, and I will see you in class.